Hi, my name is Suzie Pun. I'm a professor at the University of Washington, and I'm also going to talk about biomimicry, using materials to mimic things in our body for medical treatments. One of the inventions that my group has developed is polystat, which is a polymer hemostat. So it is a polymer that we can inject and it will stop bleeding. And we developed this for use in trauma, together with an emergency medicine physician, Nathan White. Trauma is actually the #1 cause of death of young people in the United States. This results from automobile accidents, from falls, from workplace injuries, or from acts of violence. And because it preferentially affects the young, it accounts for more years of lost life than either cancer or heart disease. It turns out that about 35% of pre-hospital deaths result from uncontrolled bleeding. So the patient basically loses too much blood before they can reach the emergency room. So Nathan and I got together to design a material that first responders could use right on site to help stop bleeding and stabilize the patients while they are being transported to the hospital. So how do we do that? And again, we look at nature. And so we look at how we normally stop bleeding, and that's through the formation of clots. All of you who have injuries will form a clot that will rapidly stop the bleeding. And these clots are formed from fibers that polymerize, proteins that form these fibers that are then cross-linked. So cross-linked means that they're then connected to each other, and that makes them really strong. The example I'll give is taking strings and connecting them together to form a net. The strings themselves are not very strong, but once you connect them together, they can hold a lot of things. Now, the problem for us is that when we bleed, we lose the ability to form these cross-links because the protein that does that is in our blood. Okay, so it's kind of a catch-22. So what we developed was a synthetic polymer that acts as a cross-linker for our bodies. So we can inject it into the blood, it finds the forming clots, and then it will actually cross-link them and make them really strong. And so what we've seen is that our polymer can increase the strength of clots by over 2 times, and it makes them last much longer. And that's really important because that's the transit time that it takes to get to the hospital. And so the next slide will show a video where we have a normal clot on the left, a control with just a control material, and then a clot that's actually treated with our polymer. And you can see the degradation taking place as the clot is breaking down, and you can see that treatment with our polymer really slows the breakdown a lot. And that's what allows these clots to last longer. And so we've been able to test this in a rat trauma model. This is a lethal model. And we simply show that if the rat is injected with our polymer after injury, we significantly reduce bleeding because they're forming really strong clots. And that's shown here on the left. And furthermore, we get complete survival. So normally this is a lethal model. We make 1 injection and all of the rats survive the injury. So we kind of think of this as an injectable tourniquet. So when tourniquets were invented, these are things that you can apply externally to stop blood flow. Survival due to injuries in the extremities, like the arms or the legs, increased significantly. So if you look, for example, at statistics, there are very few lives lost due to external injury now. The injury is actually due to internal bleeding that people can't find and stop the bleeding. And so what our hope is that we can develop polystat as something that you can inject into the blood, and it will act as an injectable tourniquet.